Hi, Srini, how are you?
Hello.
Hello, how are you?
Hi, I'm fine, sir.
What do you do today?
Huh?
Do
I
you,
had another tuition, sir.
you got class in the morning?
No, the tuition.
Let me just adjust. I'm still too soft, can't hear you.
Now can hear?
Yep.
Okay. And today I had tuition, sir.
Oh, you got tuition today?
No, I had already.
Oh, you had already. Okay. Anything you want to ask?
No. So today chapter 6, right, sir?
Today, chapter 17, yeah.
Okay.
So
Can
your
learn
teacher
new
has
chapter today.
completed lah.
Yeah.
Huh? So fast ah?
I told you much, sir. Then you say no, we go
I
slow. Like,
know.
what's the point going fast?
No point in going so fast.
Oh, he just go only lah. The teacher.
How did you manage to teach so fast? Okay, let us start. Sorry, lost my slide. Something went wrong. Just give me a little while. Something went wrong. Very slow, very slow. I'm looking at PowerPoint. Why so slow? Okay. Let me just record. Let me just get it record and we can start. Okay, let us go to electromagnetic induction. Topic 17. We will start with magnetic flux. Basically, just same. We study magnetic field, just a different line. So flux is just the total number of lines passing through the area. Okay. Start this formula, dA. And we will go to Faraday's law and Lenz's law. That is the experiment we'll go through. Your STPM work, and then we go to self-induction, where we close the switch. There's your coil there, there's your battery. The current will start to rise. So we apply Faraday and Lenz law to tell you that there's an induced EMF opposing the rise of current. And energy stored in inductor. Right? Inductor is just a coil. Then mutual induction, where instead of having a coil where you're changing current, we have another coil there. So the current passing through here will produce a field that passes through a second coil. So it will induce an EMF there. So that is called mutual induction. Okay, so that is your value of constant that you need to remember where to find your permeability. Okay, let's go to the syllabus. Electromagnetic induction, magnetic flux. We need to define it. Right? They show you a big dot, so it's a scalar product. Faraday's and Lenz law. State and use Faraday's law and Lenz law. Derive and use the equation for induced EMF in linear conductor. That means a straight conductor and plate coil in uniform magnetic field. Okay, let's just review what we did in chapter 16. We have a conductor that is moving. We have the fixed rail there connected to a battery, and you have the field. So basically, the conductor is horizontal, the field is vertical. So here we look at when we turn on the switch, the current will flow. Where's the direction of the force? Or where's the motion of the conductor? Yeah, Trini?
Okay. So current is going to the left.
Current is going inside. Learn to read. Here we are interested in this one. We are looking at the conductor here. This conductor. Right? This conductor. So you must be able to read the current is going in. It's coming from here. And going in.
Force is to the right.
Sure.
Yeah.
Okay, good. Force is to the right.
I still not sure how to read the current only.
Okay, current from here. Positive terminal. Come out here.
Okay.
So we are interested in the rod, in the moving conductor.
Oh, not the whole circuit lah.
No, we're not worried. This one is just to tell us how the current flow. So we are interested in the motion of the rod. So concentrate on the rod. Don't look at the rail. Right? Whereas here, there's no battery. There's a magnet. There's a field. There's a conductor. So here we move the conductor up. Then we see a current on the galvanometer. Okay. So topic 17, the conductor moves in magnetic field. The conductor becomes induced EMF. I mean, in the conductor is an induced EMF, a source of power.
So just give me 1 minute. Go back in.
That means the conductor becomes a battery, if you like.
Okay. So the topic 16.1, force on a conductor carrying a current in magnetic field. Source EMF required, that means a battery required. here is like there is no need battery because the conductor itself is a battery itself,
Same,
right?
we have a battery, we have conductor, then it is moving. Now we replace that battery with galvanometer, but we move the conductor.
It's like backwards lah, basically, right?
Do backwards, and we have a EMF here.
That means
That's
like
all.
reverse process lah.
Yeah, reverse process.
They do have the EMF, but then it transfers back to the battery.
The EMF is in the rod itself. Okay.
Then the battery?
No need battery already. Battery we replace with a galvanometer.
Oh, so in this case, you just need the BF and the rod, the conductor, which is the current.
You just need the field and move the conductor. Then you have a current flowing already in the circuit.
Oh, without the battery help lah. The other one needed battery help.
Without battery. Right here, without a battery.
So the only difference means the other one with battery, the other one without battery.
This one need battery. Then you have a motion. Three things. You got field.
Okay.
You got motion. You got current.
Oh, because you connect the what is that? The galvanometer to the what's that? The conductor. That's why it starts producing current.
Becomes the galvanometer, and we give the motion.
Oh, battery is the galvanometer.
We have the field, and we have the current. No, the current is called the induced current. No.
Oh, okay.
Whereas this one is the direct current. We provide the current. We provide the field, then they have a motion. Whereas here, we provide the field, we provide the motion, then you have the current. Okay?
Okay.
Okay, we'll define some terms there, magnetic flux. Right? Basically, why we study electromagnetic induction, because it provides a basis of an important means of generating electrical power. Right? So we are going to look at the laws of electromagnetic induction. Okay? That is your core power. Basically, you heat the water, it becomes steam, turn the turbine, turn the generator, and then you have the electricity coming out. Okay. And what is missing in the picture? This is your battery. That's your conductor. That's your mercury. So your battery is connected to the
conductor is the one that is moving, right?
Yeah, conductor is the one that's moving, the black one. And then you're connecting to the container there.
Okay.
So what is missing?
Magnetic field.
Good. Magnet is missing. You
Yeah.
need a magnet. Without magnet, it won't move.
Yes.
Yeah, good. Right? In induction, the word means to bring about. Right? Our motion bring about a current from some other form of energy. So in this case, our motion is mechanical energy converted into electrical energy. So galvanometer, because the current is very small. So galvanometer is used to measure small current, and it can measure in both directions. It can either move up or move down. Right? So in this case, it's mechanical energy, motion of the rod, to electrical energy. So first, you will see every topic, we will define new term. Okay? These are learning English. You have to learn new term, new vocabulary. Magnetic flux is the product of magnetic flux density and the area normal to the line of the flux. Right? So we want the flux, magnetic flux density, that's the area around it, A. So we represent it with a new symbol, phi BP. Right? So in this case, that's the area, it is perpendicular, that is BA. BP is the perpendicular component of B. That means wherever it's not at, it's an angle, we want to look at B that's perpendicular to the area. Right? In this case, this one, B is at an angle to the surface, theta. So we draw a rectangle, find the vertical component, this one, that's perpendicular to this area. So this one is B sine theta. Then we can use this formula, BA sine theta. That vertical component times that area. Right? Writing in vector equation, magnetic flux is a scalar product of magnetic flux density and area that the flux pass through. Right? So there is a dot here. Right? Dot here. A points outwards. So vector A usually we consider as pointing outwards in the normal to the surface and perpendicular to the area. Right? So it's a scalar product of B and A. Right? So if we are going to write properly, it's a scalar product.
Go back again, sir. What you said?
This one I just explaining to you. It's a scalar product.
Okay. Magnetic flux, scale. The B
This
is
is
the
a scalar.
product of magnetic flux.
These
Yes.
two are vectors, B and A are vectors.
Yeah lah, vector kali vector is to get scalar lah.
So, in this case, right, you want to write as a vector as a scalar product, B dot A point outwards. That's your A. That's your B. And in this case, the angle is between the two vectors, alpha. Right? So it's BA cos alpha. Right? So wherever you see a cos like that, and the angle between them is alpha. Right? Alpha is always the sine. Alpha is always the angle between the vector. Okay, so this formula is for vector product. You want to use it as a vector.
So, but will they have sine theta one?
Sine theta one, if you don't bother about the vector product, you basically use that
you
definition.
Mean like sine 90, yeah?
You basically use that definition. That means you want the perpendicular component to the area, the product of this VA. So in this case, you have to, that angle is theta between the B and the area, theta. Okay?
Okay.
Usually university, we won't bother about all this already. We will use vectors. So that's probably the reason why you all introduce it in Form 6. Okay, so either you use it as a scalar product, and in this case, the angle is alpha, not theta. We look at this angle, alpha, rather than this angle, theta. Okay. Okay, unit, B times A. B is Tesla. A is meter square. So instead of calling it Tesla meter square, we call it Weber.
Oh, Tesla meter square becomes Weber. Okay.
Yeah. So the unit of flux, magnetic flux is the Weber, WB. 1 Weber is the flux density on the unit area. Just call this one A1, where magnetic flux density passing through is 1 Tesla. This is 1. This is 1, right? Or 1 Tesla times 1 meter square. Okay, it's just general knowledge for you. Magnetic field of the Earth is 30 to 60 micro Tesla.
So back again. Wait, 1 minute, sir. That means they're trying to say magnetic
area.
flux.
This is the area. Meter square is the area.
So BP is the magnetic flux density lah.
BP is the magnetic flux density.
Yeah lah, passing through it is 1 Tesla. Wait, TM -2 is their unit. So TM square is their unit. So the magnetic flux density is the Tesla lah.
Yeah. Instead of call it Tesla meter square, we call it Weber for magnetic flux.
Oh, okay.
Right? Another term, magnetic flux linkage. Right? If the flux enter the coil at an angle, like in this case, a normal, then we get our VA sine theta. Right? That's an angle, or it can be in this case, right? Enter at an angle theta. Right? That's for one turn. If there are one turn there, then VA sine theta. If there are entrance, remember all these flux will enter through each turn in turn. So it will enter entrance. So we call magnetic flux linkage.
Wait, sir, repeat again, sir, what you meant.
If there are entrance, then all these flux, all this magnetic flux, all this magnetic flux density, each of this line will pass through the entrance as well. So we give that total core magnetic flux density is the total flux passing through entrance of a coil is the product of flux and the number of turns. And
so you're trying to tell means one magnetic flux passing means is BA sin theta, but then like a lot passing means is called magnetic flux linkage lah.
If it's one turn, that's your BA sin theta.
Yes.
If it's n turn, then we call it magnetic flux linkage.
So like many turns means so linkage lah.
So one turn, there, n turn, we just times n.
Solve.
Bend the person from class, kick the person out of class, bend it. Make fun of it, then you can memorize the formula. BAN sin theta.
Yeah, this is more fun. Sir.
Okay.
Understand.
Or you prefer another way, NAB, up to you. Just write the way you can remember the formula.
No, bend lah, bend the person.
Bend the person easier. And remember where is the angle? Angle theta is this one. How to visualize the two? How to picture the two of them? Magnetic flux density B, number of field lines passing through a region per unit area in a particular direction is a vector quantity. Magnetic flux is the total number of lines passing through the area A. It's a scalar quantity. Okay? That's the difference between the two. One is the number of lines passing per unit area. That's your B. Flux is the total number of lines passing through that particular area.
Wait, but what's the difference between B and A?
There's a difference, no? One is number per
I don't
unit
get it, but both
area.
same. The
number per unit area. That's all.
Same.
Number per unit area. This one is the number of lines passing through the total area. That's all. This one got direction. This one no direction.
B means number per unit area, not the total area, right?
Yeah, number of field lines passing through a region per unit area.
That means a small section. Is it?
Right? Number per unit area, whereas this is the total number passing through the area.
You mean the total line passing through the area is A and a certain one for B, right?
B is just the number per unit area in a particular direction.
Just sound the same only lah.
Different per unit area. One is the total number passing through the area, one is per unit area.
Per unit area, through an area. So through an area is bigger, right?
Through an area means more lah. Per unit area, basically, you are just dividing. If you like, you can think of it as a you can think of it as a this one divided by area, no? If that will help you. Right? One is a vector. It gives you the number of lines passing per unit area. The other one is the total number of lines passing through that area. Okay, never mind. You go back and think about
A
it.
one is the total thing. B is like a small
It's
thing.
just new things
right?
that you have to remember. So you have to learn to accept that. You can use your time to go back and review that.
Okay.
For material other than air, right, then we have to introduce the term relative permittivity, mu r. It's not mentioned in your syllabus. Just in case you are required. Right? We just multiply by mu r. Right? Mu r is usually for ferromagnetic material is about 7,000, very high. That means increase the flux, the magnetic flux linkage by 7,000. So soft iron core in electromagnet increase the magnetic field strength greatly. That's the reason why you feel magnetic. You put a iron core in your electromagnet. Okay, try this question. We have completed one section. So try question. What is the answer?
Teacher, the meter unit means it's basically 10 to the power of -3, right?
Yeah. Milli Tesla.
Okay.
10 to the power minus 3.
Yes. So Tm square.
Changes to meter square.
Okay. So, Tm square.
Just basically getting you to remember to play with the formula, to force the formula into your head. That's all.
Yep. No. Sir, don't show yet. Don't show yet. I'm trying. Wait, 1 meter 100, so it's square, so like 84. Is the answer 1.12 times 10 to the power -6?
No, 1.3 and 10 together, -6. So some calculation mistake somewhere.
Oh, I put cos 50.
Okay, careless.
Teacher, I put the other correct, but I put cos 30, not sine.
Okay. Must be sine. Must be sine.
I thought I saw just now the formula was cos. Maybe my mistake.
Don't get confused. That's why you don't look at the formula carefully. That's the problem with you.
Okay, got it.
And then the syllabus doesn't help. You try to introduce too many things and then you get you all confused.
That one was cos. That one was cos one. How come suddenly sine? That slide.
You must know what formula you are using. This is theta here. When you memorize formula, you must memorize it, understanding where is the theta.
Oh.
Okay. Okay, we have to change the new zoom soon.
Okay.
Whereas if you are going to use vector, in this case, then this is your alpha. Right? Between the vector is the angle called alpha. Right? Don't get confused. So you choose one of them. But your syllabus prefer to use this one. Okay, B dot A, which is BA cos alpha. Okay, this is the angle between the two vectors, alpha. Okay, so we have completed this section. Okay, so all these formulas you need to remember. Try this one in your book, page 220. In your book, page 220, number 2. Yeah, what's the answer?
1 minute. A.
How can it be A? Got Antons.
Oh, no. C.
Right? Basically, the angle is between the, here is the normal and that, but you
Yep.
depend on which formula you are using. So if you are using this formula, then you must go and find your theta. Right? Your theta is between the field and the area. So it's 90 minus alpha. So you get cos alpha.
Oh,
Right? Remember your maths there. That's your maths. Okay.
No. Just wait for a minute.
Okay or not?
Yeah, 1 minute answer. Wait, so sine 90 minus alpha means is sine 90 cos alpha minus cos 90 sine alpha. Is it?
So it becomes cos alpha. Okay, that's your maths there. You can go and try it out. This is 1. This is 0. So you get cos alpha.
Oh, so yeah, okay, makes sense. Okay, thank you,
Or
sir.
if you use the vector method, it's faster. Vector method, you get the formula straight away. BA
Yep.
cos alpha, BAN cos alpha straight away. Right? There's your area. There's a vector for area. That's your field. So there are alpha is that angle, depend on which formula you use. It's up to you to choose. Okay, I think we'll stop here. Give you 5 minutes break. Okay, 5 minutes break. Then we start a new Zoom rather than stop halfway.